Okay, this concept is about how to read and understand heating and cooling curves and be able to use them to calculate heats. So on a heating and cooling curve, it's a diagram that represents a constant heating. So remember, a constant heating or cooling of a substance. And our axes are temperature and time. And there are three different areas on the heating cooling curve, regions. One is there are going to be some slants, and the slants are where only one phase is present, and I'll talk more about that on the next slide. And the second place is, or the second characteristic of the curve, is a plateau, and in the plateau there are two phases present. And again, I'll talk about that in a few seconds. And we have to understand that the potential energy changes on the plateaus and the kinetic energy changes on the slants. Okay, so here is a typical heating curve, and this one happens to be for ice or water, H2O. And what I'm going to show you here is, as you can see on the, here, it's the axes are here. Here's the axis 1, and then here's axis 2, and what you can see is the curve looks like a slanted staircase as we go up the curve here. And the other thing I want you to notice is that there are slants to the staircase, and then there's these plateaus, right? And I mentioned those before. And there's different things happening on each one. So the slants, let's just draw that slants here. The slants have two phases associated. The slants have only one phase associated with them. So that's only one phase, right? And then on the plateaus, which is here and here, we have two phases, right? And so what's happening on each one of those is on the slants, we're taking heat energy and we're converting it to kinetic energy. And then on the plateaus, we're taking heat energy and we're converting it to potential energy. And remember, the potential energy and the heat energy, or the kinetic energy, are different things, and we can convert one to the other as we do this. Okay, so let's look at the next thing here. And I didn't want to do that. And so let's look at the next thing here. And we want to be able to understand what's going on with each one of these things. So as I mentioned before, we can use the heating and cooling curve to understand problems that are happening as we do this. And let's look at what's going on here now. Okay, so in this section here, the only thing we're doing is heating the ice up, so heating the solid up. And in this section, we're converting that heated solid to a liquid. And then in here, we're moving the liquid we're heating the liquid up until it's ready to boil, and then we're doing that here. And then now that all that boiling has now resulted in the last phase, which is gas. Now, a couple of points you have to look at here is the first point is our melting point, and that's going to be right here, right? And you can look back here, and that's the temperature of melting, and for this case, as we know, it's water, so it's going to be 0 degrees C. So this is a T melt, and here, and this is our melting point, okay? And then here's our boiling point. This is where we start to see vapor, and if you translate it all back, you get T boil, or T vaporization, and that's going to be equal to 100 C. Okay, so those are the two key points there, because we're starting to see. Okay, now let's look at what else is going on. Okay, so we talked about the kinetic energy, we talked about potential energy, and how we can use this thing to solve problems. So the way you usually solve these heating and cooling curves, if you were asked to, let's say, bring some ice from, let's say, this temperature here to this temperature here, the way to do it is to, instead of trying to write a long equation for all the stuff that's happening in here, what I usually do is I break it up into sections. So here's a section, here's a section, here's a section, here's a section, and section 1, 2, 3, 4, etc., 5, and then you calculate the Q for each one of the sections. So Q1, and then Q2, and Q3, etc., and you add them all up and to get Q total, right? So solve each one of these in a different each section one by one, and then you don't have to worry about trying to figure out what's going on with the thing here. So, okay, so let's look at what we're doing here. And so there's a couple of key things that you have to remember when we do this. Each one of these areas here, this fusion and this vaporization, they have different specific heats for this process. And let's look at first one of what they are. So the Q fusion is going to be, for water, it's 334 joules per gram, and that's going to be the H fusion. And then for vaporization, which we call H vaporization, that's going to be equal to 2,260 joules per gram. All right, so that's going to be for the value for here and here. This one is for here. And for all these other ones here, here, and here, you use this specific heats. And for water, remember for the liquid water, it was 4.184, right? 4.18 for water. And for steam, it's 2.0. These are all joules per gram, the steam. And for solid or ice, it's 2.09, right? So you will have to know that for each one of these, you're going to have to use the correct value for the equation when you put it in here. Remember, for the equations for the slant, so it's going to be Q equals MC delta T, and for the other parts, the plateaus, it's going to be Q times H times the mass. And H will be either the H vaporization or H fusion. Okay, so let's move on and show you how we can use this on the next slide. Oh, one more quick thing while I erase all this stuff. One more quick thing about this this part is that, remember, we're adding heat. So when we do this process, when we go from here all the way up to here, we're adding heat. So we're adding heat. So this is all add heat. And when you add heat, you make the whole process is endothermic. You're adding heat to the system, so it's endothermic, right? Endothermic. So this whole process from here to here to here is endothermic, right? And you just have to remember that heating is an endothermic process. Okay, so here's the flip curve of that, or the opposite curve of that, and this is a heat cooling curve. And everything is exactly the same as far as what's happening on each one of these, except instead of adding energy or gaining energy into the system, we're losing energy, or we're getting energy back from the systems because we're going down in temperature. So in this case, this is an exothermic reaction, exothermic process. All right, so everything else is the same. You calculate the heats the same way. So in this one, and this one, where there's one phase, we use the Q equals MC delta T, right? That's that process. And in the other one, the other area, we use this equation. Let's do that. This equation here, which is Q equals heat of fusion times the mass, and that's for here, and then Q equals heat of vaporization times the mass here. That goes here. Now, the only difference is that in this case, the heat of fusion and the heat of vaporization are going to be negative values. So this is going to be a negative 8 HVAP because we're losing that heat. That the heat is being given away from the system into the surroundings. So it has to be negative. The negative doesn't mean it's negative heat per se. There's like as less than 0. It just means the direction the heat's going. The heat is going out of the system, right? And in both cases. So remember, in this case also, it's going to be a negative H fusion, right? Because we're losing heat, right? And so the Q will be negative here when we do this calculation. And the other things with the Q equals MC delta T, because T is T final and T initial are going to be, T initial is going to be greater than, T initial is going to be greater than T final. When you do this calculation, you're going to get a delta T is going to be a negative value. So that'll make your Q already negative, right? Because mass can't be negative. The C is not negative. But when you say, let's say you go from 100 C to 10, so it's 100 minus 10, that's going to be negative. Okay. So let's just quickly clean this up a little bit and then just show you something else that's happening. So we told you that the values are going to be negative. So let's just put them in right now, right? And so this is going to be minus 2260 joules per gram. And here it's going to be minus 334 joules per gram. Right? That's a 4, right? And so when we do our calculations, we're going to get this energy back, right? And the same principle here is happening on the slants and things. So let's look at the slants real quick. The kinetic energy is being converted to heat energy here. So all the molecules that are moving around and flying all over the place in the gas, all that energy is lost. We get that energy back, and it's converted to heat energy, right? And then the same thing's happening on the plateaus. The heat energy that's in here right now is going to get converted back into, it gets lost, and the potential energy gets converted back into heat energy, right? So in this case, the potential energy and the kinetic energy are all going to heat energy. And in the previous case, the heat energy that we're putting in all goes into kinetic energy or potential energy. So there's not really much more to say about this. So then remember on the C's, the C values here, let me just erase some of this stuff to make it clean it up a little bit. Remember that the C values for here, the specific heat of the solid is going to be, I think it's around 2.09 joules per gram degree C. Let me just write that a little better. 2.09 joules per gram degree C. And then the vapor one is going to be 2. So this is about 2.09 joules per gram degree C. That's a 2. And up here is going to be 2.0 joules per gram degree C. And here, remember, it's 4.18 joules per gram degree C. Right? Or this one is also 1 calorie per gram degree C. But if I'm going to give you anything, I'm going to mostly give it to you in joules, right? So you have to look at these, and I won't tell you to memorize those numbers. You will be given those numbers on a quiz or a test, but you need to know where to apply them again. Okay. Okay. So now we know the parts of the curve and what's happening on each part of the curve. Let's use this curve to show us how we would solve a problem if we're bringing some solid ice up into a heated vapor. So let's, for our demonstration purposes, we're going to take 100 grams of ice at minus 10 degrees C and convert that all to steam at 115 degrees C. And so I've given you a lot of the variables that we, and a lot of the constants that we need over here. So let's use let's use our approach. Okay, so for what I've been showing you before is we should set this up into several things. We're going to set this up this way. We're going to calculate the energy needed for this to do this section, this section, this section, this section, and this section here. So here's one section. Here's a section, here's a section, here's a section, and here's a section. So let's calculate how we do that for each section. Okay, so get some of this clutter. I'm going to erase some of this stuff. We already know what our problem is. And now we're going to start to break this down into a manageable problem. So we're going to do our first section here. I'm just going to write that right here. So section 1, and we're going to calculate that right here. And that's going to be equal to Q equals mc delta T. Okay, and we are going to put in, we have 100 grams of things, so it's 100, and then we're going to put the C in that particular case is the ice is going to be 2.09, and then we have a change in temperature of, remember we said we started at -10 to 0, so that's going to be at +10. All right, and that equals the total Q, and if you do the math here, you're going to get 2,900 joules. All right, so let's do some erasing here. All right, and now our next section is going to be this section right here. Let's just do this section here. So this one here to here, and that's going to be the following. Let's do that right now. That's going to be, now this is a different equation. It's going to be Q equals, and then heat of fusion, and times the mass. And so that's going to be equal to 334 times 100. And so that will be equal to, that's going to be equal to 3,3,400 joules. So far we've got section 1 and section 2 done. All right, so let's erase some of this stuff here. Give us more room to work. Okay, I have to rewrite that again. Hold on. That was 3,3,400 joules. Okay. All right, so now the next section is we're going to heat the water up, so that'll be this section here to here. And we already know the Q for that because we've heated water before. It's going to be equal to Q equals to 100 grams, and then we know that's 4.18, and then we know it's going to be 100 more degrees C. That's the delta T. That's the delta T because it's going from 0 to 100. Right. All right. And so that was going to be equal to. That's going to be equal to. The value there is going to be equal to 41,800 joules. All right. And so that's good. So we can erase this. We've done that one. And the next step we're going to be doing is the following. We're going to be going along this part here. And we know that Q for that is going to be equal to heat of vaporization times the mass, which is 100. And that's supposed to be mass. I'll just put that down so just for clarification. Mass, which is 100. And then if we do that, we're going to get 226,000 joules. Okay, and so, and then the last thing we have to do is our last section up here is heat the vapor to 15 up 15 degrees, or from 100 to 115 degrees, and that's going to be equal to Q equals mc delta T, and we need to use the C for the steam here, and we know that T is going to be 15, so that's going to be a 2, and then the mass is 100, so that's going to be 3,000. And so far so good. So everything we've worked out, we've got all the sections done now, and now we just have to add up the individual things there. So let's add them up. And if you add them up, you're going to get 306,000 joules, roughly. Right, there's a 90 in there, I didn't put that in. But that's going to be equal to 306 kilojoules. Right, that makes sense, right? Because we've added 100 grams of water, and it takes you that much energy to put all the way up to steam from here to here. And so if you've got that and you tried it, good job. If not, make sure you understand how we calculate the heat in each section, and you should be good to go. And one more thing before this, if we had done it the other way, if we had gone from, let's say if we had gone from here back down to here, everything is the same process of going from here to here, except the heat that we get back, all these heats will be negative because we're getting heat back, right? This would be a cooling curve and we're getting heat back. So our answer would be it's minus 306 kilojoules, indicating that we're getting heat back, or you would say we acquire or we get back 306 kilojoules in your answer. All right. So hopefully this has been a helpful tutorial, and now that you understand the different parts of the heating and cooling curves, what's happening on each little step or slant or a plateau, and what's going on, you understand a little bit more about the differences in the specific heats associated with each individual area. And for example, heating up the solid, it has a different specific heat than heating up the liquid, which has a different specific heat than heating up the vapor. And also that the heat of fusion and the heat of vaporization are totally different numbers. And that knowing how to use each one of those specific variables, you can use them to calculate the heat associated with each one of the sections in the heating curve. So section here and here and here, and then when you're done, you can add them up to get your total heat that you need to either add or total heat that you get back from doing the process.